Okay, welcome back. So we now have students talk.
Hello, good evening, Adhish.
Yeah. So Professor Amitalok Butkule will chair this session. So let me introduce the chair. He is the professor in the Department of ECE at IIT KGP, IIT Kharagpur, and his research interests are in information theory, coding theory, and information theoretic security. Amitalok, take it over.
Yeah, thank you very much. Thanks, Adrish. And thank you everyone for being here. It's been a very nice couple of days. This is the third day, so I hope you're enjoying. So today we have a couple of very interesting talks. Technically, the student talk is not really by a student, it's by Deekshith. He's recently graduated, he's defended his thesis a while back and now at Samsung. So Deekshith, can you hear me?
Hi, Amit. Yeah.
Hi.
Sure.
Okay, so are you okay? Shall we start then? I'll just introduce you. Is that okay?
Yeah, sure.
Okay, great. Okay, so thank you everybody for being here. So this is the first talk, and we'll follow this with the other young faculty talk. So Deekshith, Dr. Deekshith PK did his BTech at Electronics and Communication Engineering Department from the Government Engineering College at Thrissur. Then subsequently he was at IISc, where he worked with Professor Vinod Sharma, and worked on information theoretic analysis of point-to-point and multi-user channels, with specific focus on energy harvesting, and later on finite block length constraints. In fact, that is going to be the subject matter of his talk today. Post his PhD, Deekshith joined the Samsung R&D Institute at Bangalore, where he's currently focusing on, and he's a part of the mobile battery division. So today he's going to talk about some of the interesting things he figured out in his thesis in particular, and most likely continues to work on those things. The title of his talk is Finite Block Length Rates over Fading Channel with an Energy Harvesting Transmitter. So a lot of interesting things in the title, and we look forward to the talks. So Deekshith, if you're ready, you can maybe just quickly share your screen once.
Yeah, sure.
And then you can take over. Yeah.
Hi, I'm Deekshith from Indian Institute of Science, Bangalore. I thank the organizers for giving me an opportunity to present my work. This talk is on finite block length analysis for a wireless channel powered by an energy harvesting transmitter. This work was done jointly with my doctoral thesis advisor, Professor Vinod Sharma and Kunjiti Gautam Shenoy of Indian Institute of Science, Bangalore. The context of this work is as follows. Suppose there is a manufacturing setup wherein various sensors are deployed for environmental monitoring or say for inventory management. These sensors collect data and report about the device operation to industrial controllers. Now such industrial control networks currently use Ethernet-based transport. However, to enable advanced automation, 5G new radio is soon expected to support such communications in an industrial network. For such a setting, reliability and latency of communication are quite important. In addition, periodically replacing the batteries in these sensing units is not quite practical. However, harvesting ambient energy is now a mature technology. So, putting all these things together, we have a scenario in which a transmitter is harvesting energy from an ambient source and needs to communicate them wirelessly within a given delay and reliability constraint. And this should be subjected to the constraints imposed by the system, like the average harvested energy, average probability of error, and maximum permissibility rate. We are interested in characterizing the maximum rate of communication in such a setting. Now, what is the standard solution available for such a problem? Well, we can characterize the capacity of the channel, which is the maximum rate, as the probability of error tends to 0 and simultaneously the delay tends to infinity. There are primarily two notions of capacity that is associated with a wireless channel. One is what is known as the ergodic capacity of the channel. Now, this is a capacity in the Shannon sense, and it is obtained as it is expressed as an average rate, averaged over the fading distributions, and it can be achieved using code words of reasonably large length. Now there is this other notion of capacity what is known as the delta outage capacity. This is not a capacity in the strict channel sense. Now, we say that a wireless channel is an outage if the channel gains are too low, and accordingly the overall signal to noise ratio is too low. Now, suppose we are willing to stand an outage for, say, delta fraction of the transmission times. Now, delta is a small number, positive number. Now, this delta outage capacity, then we can define it as the maximum rate such that the probability of the channel being in outage is at most delta. Now, the problem with these notions is that though they can give convenient expressions for maximum rate, to transmit at these rates, actually the code words many a times would need to be quite large, perhaps larger than the delay constraint that is imposed on the system. This is because inherently the capacity is an asymptotic quantity, asymptotic in the block length. Further, capacity is characterized by taking probability of error tending to 0. So, if we would like to have expressions for rate for a non-zero probability of error and a strict delay constraint, we need more refined metrics. So the exact quantity of interest in such a setting is the following. We call it as R star in epsilon. It is the maximum coding rate at a given code word length n. So this is a proxy for delay in the physical layer code word length. Now, and probability of error epsilon, subject to the constraints, the power constraints that is imposed on the system. Now, the problem is that computing this, it can be shown in many cases, it has been shown in many cases that complexity of computing this R star in epsilon is prohibitive. So, it is not desirable, it may not be possible even to get a convenient expression of R star in epsilon. Such a scenario, it was shown in this 2010 work by Polyansky-Pourvoudou that for many channels of interest, this R star n epsilon can be reasonably well approximated by this expression that you see here. So it's called as what is known as the normal approximation, as it is resulting from a central limit theorem kind of analysis. Now, there are two terms here. First is the capacity of the channel, C. Now, there is a second term. The second term is actually a backup term for most practical settings. Why so? Because so there are three particular parts to the second term. One is the term V. There is this n coming up here, which is the block length or the code word length or the delay, and epsilon, the probability of error. Now, for practical systems, the probability of error is less than half, and hence this term, which is the inverse Gaussian series, evaluated at a value less than half. So this is going to be less than 0. It's a negative quantity. This is a positive quantity. And this channel dispersion, which we will see later, it is actually a variance proxy for the channel. Much like capacity is a mean proxy for the channel. Say for a discrete memberless channel, we know that the capacity is the mean of a certain log likelihood ratio. So the variance of that so this channel dispersion is a proxy for variance proxy for the channel in that sense. Now this is the result, general result, and we would like to obtain similar results for this channel that we show here. Now say S is the message that we would like to transmit. It is chosen uniformly randomly from a finite set. Now the encoder encodes into a code word. Now the power for sending each code word symbol is harvested from an ambient energy source. Now there is a battery that can store remaining energy after each transmission for future use. So that is shown here. We assume that the battery to have infinite capacity for convenience. This models a scenario in which battery capacity is much larger than the average energy available for harvesting, and typically these kind of systems, energy harvesting systems, has been studied under such an assumption. Usually it has been studied under such an assumption. Now the code word has to be transmitted over a block fading channel. Now what is a block fading channel? So if you see here, there are multiple blocks here as illustrated with multiple colors. So each a block is basically, it corresponds to the channel coherence time. It is the duration over which the channel gains remains fixed. Now across blocks, the channel gains changes in an IEEE fashion. Now we assume that within a block, within a coherence interval, the channel is used n subscript c times, nc times. And we assume that the total communication, the duration of the communication spans B, capital B such blocks. Accordingly, the code word length n is B times nc, and it is basically the proxy for delay. Now we denote it as n. Now we assume a coherent model. Basically, it says that the channel gains are known to the receiver. We also assume that there is perfect CSIT. Now we will show that as a special case of analysis. Actually, we can recover the results for no CSIT as well. So we'll get two results in one go. Now in the figure, E subscript BK, this is the energy harvested in the kth channel use of bth block. So there are nc channel uses within a block. So that is E subscript bk, and X subscript bk is the corresponding code word symbol. Now y bk is the channel output. We assume that there is an additive in addition to the fading. There is an additive Gaussian noise at the receiver. It's assumed to be a complex normal random variable, is Z subscript bk, and S hat is the decoder's estimate of the transmitted message. So probability of error is probability that S is not equal to S hat. And our goal is to obtain lower and upper bounds on the maximal coding rate for a given code word length n and probability of error epsilon, and subject to the energy harvesting constraints imposed. So broadly, the challenges are twofold. So one is that the power constraint that we consider is different from the usual power constraint that we see in the finite block length analysis. The typical constraint that is being used is the what they call as the peak power constraint, as shown here. So this is basically saying that the code word symbols are chosen from within a sphere, n sphere of radius given by this right hand term on the right hand side. Now, if you can contrast this with this expression that we have here, so there are a total of n constraints that we have because of the energy harvesting mechanism. So energy harvesting basically introduces the time varying and a random peak power constraint. Basically, the way to interpret this is that because of the energy harvesting mechanism, you have n energy conservation equations. So these are basically energy conservation equations. It's saying that the total energy that you can use is at most the total harvested energy. Now, so that is one difficulty. Now, the second difficulty is the following: that there are works on finite block length analysis for finite state channels. Now, such an analysis cannot be directly applied to a case as the fading channel that we consider can have uncountable states. So we'll have to come up with a new analysis to tackle this issue as well. Now, but before we present our results, we'll just we'll note what is the capacity of the channel. With CSIT, the channel capacity for this channel is given by this expression. Now it resembles the capacity expression that you have for a canonical setting with average power constraint. Only difference is that so that instead of the average power constraint, you have this expression is evaluated for a average harvested energy constraint. Okay, so this is the usual. So this G1 square is basically the signal to noise ratio as given here, and it involves the water filling power allocation because we assume CSIT, and it is evaluated according to the average harvested energy rather than the average power that we usually see in the canonical setting. Now that is the capacity of the channel. Now, without energy harvesting constraint, what is the corresponding finite block length result available? So that is basically provided in this 2011 work by Poliansky and Verdu. It says that the rate can be approximated again by these two terms, capacity plus the back off term, and the channel dispersion is given by this expression here. As you can see, there are three parts to it. The first part is in fact the average of the dispersion of a AWGN channel with gain G1 square. Now that is the first part. Now the second part is actually the variance of the instantaneous capacity. Now this comes up because of the gains, the random gains that is there in the fading channel. Similarly, there is a third term which is also an artifact of the random gains. In addition to it has some bearing on the power constraint that we fix. Basically, this L function L that you see here is related to the Lagrangian multiplier that you get while solving for the optimal power allocation scheme. Okay, so with that, we present our first result. So that is a lower bound on the this R star and epsilon. And what you can see here is that for any alpha, so there is an extra constant that we have defined here. What you have is the lower bound has again, if you neglect the order of n terms, you have two terms basically. One is a capacity and a back off term. Now the back off term itself has two parts to it, and the first part, which is actually quite close to what you saw previously for a non-energy harvesting case, wherein one of the terms is replaced with something else which is quite close to it. Okay, and then there is a second term that is there. Now this second term, as we have explained here, you can see that the usual constraint that we have is the usual second order coefficient that we have is as if you can see the cursor, that is this, and the second term that you can see, that is basically an impact of the weight and transmit scheme that we use in our analysis. Now because so basically what it says is that you have the transmit in our analysis, we wait for the certain number of slots, the initial slots, the transmitter waits without transmitting. It just harvests energy so that it has enough energy for future transmission. Now because of that, there could be a potential rate in loss. This term here actually characterizes that particular rate loss. Now our second result is the following: upper bound, and the second order term here is actually quite close to the dispersion term that you have for the non-energy harvesting case, and in fact it can be seen that the maximum difference of both these is at most 1. Now we will quickly highlight some of the key ideas that we use in our proof. So basically one key step is decoupling coding from the water filling or control. So by doing so, we convert the actual channel with gain HB to an equivalent channel with gain GB. So recall that GB is the SNR. So it has the power allocation term also in it. Now, once you have that equivalent channel, you are able to choose code words from a sphere of an appropriate power, and then we can work with that. So this actually gives a convenient way to analyze the problem. Now, once we have that, as we have mentioned earlier, we we use this policy where the transmitter waits for a certain duration of time, and that is basically given. It's a multiple. It waits for a square root of n order of slots before transmission. Now it involves some analysis, but it can be shown that this probability of error in decoding, basically this can be upper bounded for any alpha by these two terms. And the second term basically that you see here corresponds to the probability that enough energy was not harvested in the initial waiting slot. So that is that. And when it comes to the upper bound, we start with a Metaconverse that is provided in the 2010 work by Deekshith et al. And we incorporate energy harvesting constraints and equivalently write the Metaconverse in this form. So this can be directly obtained from the Metaconverse. And so there is a parameter gamma n, and it is in terms of an auxiliary channel that is typical to this Metaconverse analysis. Now there is this probability term that is there in the denominator. To analyze that term, we use what is known as the strong approximation principle. Now, using the so basically, strong approximation principle we have shown here. So it is actually a invariance principle, and it basically is a refinement of central limit theorem. And as you can see, to compare it with the Berriesian kind of bounds, you can see that there is this is a probability term, and it is bound on the maximum of partial sums of random variables rather than the full sum of random variables, as you will see in the Berriesian theorem. So in that sense, this is a refinement. So we use this particular result to further analyze the probability term. Now that is about the key steps involved in proving. Now we just quickly illustrate our results in numbers. So we fix these parameters in the following way. We assume a fading distribution with complex normal gains, and we have optimized the parameter alpha that you find in the input, the lower bound, and for a rate versus average harvested energy plot, these bounds are at most different by about 15%, but the difference is low for a certain regime. So this is the maximum difference. And similarly, for rate versus B, you have a difference by about 11. Rate versus the block length, you have a difference for about 11%. So, so we have basically obtained second order lower and upper bounds on the maximum coding rate for a block feeding channel with energy harvesting constraints. And as a corollary, we can actually obtain the corresponding results for no CSAT and full CSAT. So we have some CSAT in analysis. So we can recover the results for no CSAT as well. Now, the results that we have basically characterizes back off from the ergodic capacity of the channel, finite block. So that is it. Thank you.